Welcome to week 7 live session of molecular spectroscopy of physical chemist perspective. I am Marco Provo. I am a PMRF at the Department of Chemistry IIT Bombay. I am a TA of this NPTEL course. I'm taking these discussion sessions for the past 6 weeks, and this is the 7th week. Today our topic of discussion will be based on the week 6 material of the course, which is mainly based on the Raman spectroscopy and the starting of the symmetry discussion. But today what we are going to do more focus on, that we will focus on the Raman spectroscopy part and whatever has discussed. And today we are going to solve one mid-semester paper from this year's um, CH442 course, that is molecular spectroscopy mid-sem paper, which was said by Professor Datta himself. I have asked for his permission and he has granted me to discuss that problem solution with you. So let us start. We will start with the basics of Raman spectroscopy. Today we are not going to solve any assignment problems. Assignment 6 and assignment 7, we will solve it together when we will discuss the symmetry problems, and when I will try to gather some numerical problems on the symmetry operations and symmetry elements. And with that, we will be focusing on that week only on the symmetry. Okay, now let us start with the Raman spectroscopy. So first of all, that Raman spectroscopy was discovered by Professor C.V. Raman at ISES Kolkata. So this is the biggest. This is called the biggest contribution by an Indian to the science or the scientific community. Raman spectroscopy is means become more popular after the innovation of the lasers and all. When that field booms, the laser field, then this Raman spectroscopy field also, the application of Raman spectroscopy also come into the picture. Means it got more um validation, and you can say the application part of the Raman spectroscopy become more clear. So first of all, for Raman spectroscopy, we don't require a dipole moment. Why? So because see that we already discussed that your homonuclear diatomic molecules are actually so let me write at least what we are discussing. So homonuclear diatomic molecules are actually microwave inactive. Why? Because their permanent dipole moment is 0. Now, so uh, let us ask that question in red maybe. How to get the bond length of a homonuclear diatomic molecule like a hydrogen, or suppose any other O2. How to get this? Because these are microwave inactive, because they are non-polar, right? Because dipole moment is 0. So we know that in microwave spectroscopy we get to know that rotational constant B is h by 8 pi square I c, where I is your moment of inertia and h is the Planck constant, c is the speed of velocity of light in vacuum, and this is in centimeter inverse unit obviously. So from here you also know that this is 8 pi square mu reduced mass r square, that bond length, right? From here, if you know B from micro spectroscopy, then you get to know what is the bond length. But how do you are going to calculate the bond length and other things if they are micro inactive? So your answer is Raman spectroscopy. What is happening that suppose in this molecule your permanent dipole moment is 0, right? But you can create an induced dipole. So till now what we have discussed is that Professor Datta has also told you that that in means the main so during the semi-classical treatment of radiation with matter, we actually discussed the interaction of the dipole moment, permanent dipole moment with the electric field. But there are other interactions can be also possible, but sir said that they are very weak. But one of that interaction is with the induced dipole with the electric field. Okay, so actually your um, induced dipole can be written mu I can be written as alpha E, not only alpha E but beta E square, where E is the electric field, plus gamma E cube, and this will go on. This is like a Taylor series. Okay? Now your alpha is bigger than beta, bigger than gamma. So this is the order. So to access this nonlinear property, or you can say this, so alpha is known as polarizability. Polarizability. Beta is second order polarizability, and gamma is third order polarizability. By this way it is going on, and if only in case of very light with very weak electric field, you are only limited to maybe only this alpha E. But to get access to beta and gamma, your electric field needs to be very high, and that can be obtained only from lasers. uh, so that is why the use or application of laser is coming into the picture in case of Raman spectroscopy. So but now, for now, we are only let us take with go with the mu I is equal to alpha E for this purpose, and this polarizability is actually a tensor. Tensor is nothing but an array of matrix. So actually he sir has discussed this thing, so I am not going into much thing because I am going to show you the only the quantum mechanical treatment. So for now let us consider that this we are only going to take this part, the mu I induced dipole is alpha E. Now we know that E electric field can be written as the magnitude 2E0 sine 2 pi nu L T, and nu L the frequency of light. Okay, and your alpha polarizability is can be written alpha 0 when there is no electric field, and then when it is interacting with the electric field, it is something like A, which is a constant, sine 2 pi nu mt. For now let us take this is frequency of molecular motion. Now which could be molecular motion, could be either be vibration or rotation. In case of rotation, the energy levels are very closely spaced, and for vibrational, the rotational the energy levels are actually have some difference, right? So we'll discuss that later, but for now uh, 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 the mathematics is going to be similar. So let us see what we are going to get. Mu I is actually then is a multiplication between alpha 0 plus a sine 2 pi nu mt, and with the electric field it is 2e0 sine 2 pi nu mt. So I will take maybe the second bracket. Okay, so what is this? So we are going to get, so I have done a mistake here. I will, so first part is 2 alpha e0 is constant sine 2 pi nu lt. So I have made another mistake. Sorry for that. Right. And what are the other terms? Other terms would be, there is another term which is 2a e0 now sine 2 pi nu m t and sine 2 pi nu lt. So we already actually know this trigonometric equation, that is what is cos a minus b minus cos a plus b is. It is cos a cos b plus sin a sin b for the first part, then the minus is coming. Now cos a plus b, cos a plus b is also cos a cos b, but now minus will come, minus and minus will become plus, and this will sin a sin b. So this is going to give you 2 sin a sin b, and this actually is going to cancel out. So we are going to get here, so this term will be remain as it is, and we are going to get two terms, that is cos a minus b, so that would be 2 pi nu l minus nu m t, right? Another part would be a is 0 cos 2 pi nu l plus nu m t. So actually in one case, so this is an inelastic collision of radiation with matter. Okay, so what you are going to get, so with this interaction, what you are going to see that this is actually your this is giving you three things. One is um, me highlight this. So this, when light is with the inelastic collision, what one part is, there is no change in the frequency of the light, that is known as Rayleigh scattering. And there are two things, these are known as Raman spectroscopy, Raman scattering, out of which this is known as Stokes Raman scattering, and this is known as anti-Stokes. Okay, so let me give you an pictorial overview. Suppose these are your states. For the timing, let us consider these are rotational levels. So at room temperature, these are as the energy gap is very less, so molecule is there, or all the states are populated, right? Not equally, but they are populated according to the degeneracy and Boltzmann constant Boltzmann distribution, right? So from here, when your radiation is coming, so suppose what is going to happen, that it is actually exciting your sample to a virtual state. And from that virtual state, what is going to happen, that it is going to, there are going to be two, as it is a virtual state, it has a zero lifetime. So it will not stay for, so it will go and quickly come back. So it will come back to either to suppose this, or suppose this. Suppose the light incident light frequency was nu L, right? And there could be two fates, three fates actually. One, that it is coming back to this with nu L, right? Another could be the scattering, which has a lower energy, that is nu L minus nu M, or known as Stokes Raman scattering. And another could be this one, where the scattering has a higher frequency, which is known as anti-Stokes scattering. Okay, but the important thing is there are three fits, right? As we see from the quantum mechanical treatment. Here, I'm showing you the rotational levels. So for rotational Raman, we are not going to derive the quantum mechanically the selection rule what we have done for the microwave and the infrared spectroscopy, but let us take this axiomatically, that for rotational Raman spectroscopy, selection rule is delta J is equals to actually plus minus 2. Okay, now that is why I have taken it like that on these energies. uh, Suppose this is 0 1 2 3 4. So if it is going from 2, it could come back to 2, that is your Rayleigh scattering. If it is going from 2 and coming back to 4, then this is Stokes Raman scattering. If it is going from 2 and coming back to 0, then that is anti-Stokes scattering. Now let us see what are the energy levels and what are the what from which question we have started. Our main question was how to calculate the bond length for a homonuclear diatomic molecule, as we cannot do it with microwave spectroscopy. So suppose the energy of the EJ is B J into J plus 1, right? What about J plus 2? B into J plus 2 J plus 3. So what is the energy difference? That is EJ plus 2 minus EJ. B is common, obviously. So fairly easy algebraic calculations. So this is going to lead you B into 4J plus 6. Eventually, if you take 2 outside, 2B into 2J plus 3, right? This is going to be your difference between the energy levels. So if we think this is your spectrum and this is your new bar or wave number, suppose, right? So suppose this is your 0. Now see, for j equals to 0 to j equals to 2, so firstly at this point, if it is suppose it is going from j equals to 2 or j equals to 2, then suppose let me show you first one thing. First, this energy, so this difference in the frequency is not going to depend on that what wavelength I am exciting with. So firstly, this is, let me use another color maybe. So this difference in frequency delta nu is independent of the excitation wavelength, right? Means if you excite it, means what I'm trying to say is, suppose your that difference is 50, is not dependent on the excitation wavelength. Okay, so firstly, one more thing that here what I was discussing is that firstly, when there is no difference in the wave number or energy, you are going to get intense, very intense scattering. Okay, that is actually your really scattering. Now wave number is in this side, so actually your lambda is this side, as you can see. So your actually wave number goes this means it is increasing this side. So if your energy is increasing this side, your frequency is also increasing that side. So what I was actually trying to discuss was that where your strokes and anti-strokes lines you are going to see. So you are going to see your, see, your anti-strokes have a higher energy, right? So I think I am making one mistake. Let me take this out. So suppose your wave number or energy is increasing this side, so this is your this side your scattering means it is nu L plus nu M will come this side. So suppose this is coming, this first line will come at this j equals here. J can be what? The rotational can be j equals 1, 2, 3, anything, right? So for j equals to 0, what you are going to see means when it is anti-Stokes. So for anti-Stokes, what will happen? It will go from 2, j is equal to on initial j is 2 and it will go to 0, right? So you are going to get when your j is 0, then you are actually going to get 6b. So this will your 6b. And what about then when j is 1, means 1 to 3 and those spectrums are going to come at, if you see j is 1, now means your initial is 1, now it is going to be 10b, and the ej when j is 2, then you are going to get it 14b, and that will go on. So your between between this between this, so this is actually your delta nu, right? Difference in maybe if I can use a different color, what I was delta nu. This is what I was discussing, that difference in the frequency is independent of the excitation wavelength. This is a molecular property. So this is what I was trying to say. So it is not dependent on the excitation wavelength. These gaps between the rotational levels or whatever energy levels we are taking, those are a molecular property. It is not dependent on the excitation wavelength. Okay. Now suppose our next point. So this point was made clear. Now at what gaps we are going to get the spectrums. So see, the first spectrum for rotational energy levels is going to come at, for j equals to 0 it will be 6b, for j equals to 1 it will be 10b. So means the next spectra, as we know that this for rotational energy levels there will be a maxima and then it will decrease. So this is actually the next spectra will come at 10b, next will come at 14b, these spectras. So these are actually anti-Stokes. Okay, why? Your anti-Stokes will come at higher frequency. Okay, and your Stokes spectra will come at lower frequency, higher wavelength. So this maybe the gaps are unintentionally different. This is due to my poor artistic skill, but I hope you are getting the message what I am trying to do. That the first vector will come at minus 6b, then it will be minus 10b, then it will be minus 14b. So the gaps between the each spectra is 4b, but the gap between this Rayleigh and the fast rotational Raman spectra will be 6b. So from here you are going to get the information of B can be obtained from the spectra. So and so these are anti-Stokes, Stokes, right? I hope you got it, right? The Stokes will come at a lower frequency region and anti-Stokes will come at a higher frequency region, and the gaps are dependent on this rotational selection rule, which is delta J equals to plus minus 2, right? Plus 2 is for Stokes, where there is a loss of energy. Minus 2 is for anti-Stokes. Gain of energy, maybe. Okay. And for delta J equals to 0, you are going to get Rayleigh. Okay. Now when I hope you are getting this point, right? Now when you are getting an information about B, then you will be able to calculate the bond length and all. And for that you are going to require a very high resolution spectra, right? And for this high resolution spectra you are going to use laser source. So that is one of the important thing. Now what about rotational vibrational spectroscopy? Let us discuss a little about that. Not rotational vibration, vibrational Raman, sorry, my mistake. Vibrational spectroscopy, as you know, the energy gaps I'm not talking about these gaps, but as you know that only the V equals to 0, 1, 2, 3, only at room temperature this is populated, V equals to 0. So more often than not, so if this is the virtual state and here it is not same, plus minus 1. So for here, more often than not, we are going to say either Rayleigh, so anti-Stokes Raman spectrum is very weak, or you can say less probable, because it is going more the scattering is going from vehicles to 2. Now if one is coherent anti-Stokes Raman spectroscopy, that is cars, right? Coherent anti-Stokes Raman spectroscopy. In that case, what is happening actually? Zero, 1, 2, 3. It is going to a virtual state, and then it is coming back to 1, and then another kind of, suppose this is due to new L, right? And this is new L minus new M. Now another scattering is being done using this new L minus new M, means coming from it is giving from another source, not using the scattering, and then it will go again here, and now it will come to v equals to 2. So or there will be possibility that it can come to v equals to 0, right? Then, right? So that is known as coherent anti-Stokes Raman spectroscopy. Now, even in this case, Rayleigh is highly intense, and then there is Stokes scattering. Now we will discuss that how this TMI or the cross section, Raman cross section looks like. The Raman cross section is, let us discuss it maybe here. Raman cross section. So if I am taking this P as a Raman cross section, it depends on two things. First, there is TMI of, so this is sigma. So between initial to a virtual state, and then that virtual to, it will have to come back to some psi final, right? So there is another thing. So this is what it is dependent on. Square of that, and that is delta E minus H nu. Actually, your Raman spectra is very weak, right? What we have discussed, because of the induced dipole. But now, when the condition delta E is equals to or close to H nu, then, or resonance, that is, then your signal intensity becomes very high. Why? That is your known as resonance Raman spectroscopy. Okay, so I am not going into deep in this, but if you see this equation, you can understand that from here you can also get get something like this. If I can write it like psi f sigma delta, then these are the product of two coordinates, right? Psi I have, so psi I to psi f, but it will depend on the product of two coordinates, more that quadrupole moments, not the dipole moment, but dependent on the quadrupole moment. Okay, and so based on these, actually for Raman spectroscopy, what we are actually looking at, that it is going to a virtual state, then it is coming back. If we think about uh, in case of a Raman spectroscopy, we are dealing with the downward transition from the virtual state, right? If we consider upward transition from the virtual state, it will lead to the concept to photon absorption, or mainly nonlinear optics is involved. What I'm trying to tell you, that suppose this is a state from where first we are giving it a new virtual state, and then again from here, suppose instead of coming back you are giving it another photon, means the repetition rate of the laser is going to be very high, right? And then give me the new, then you could, so suppose it is either it can go to a stationary or a virtual state. Depending on that, the lifetime of the state will depend, but when you are going to get a emission or the radiation, that will consist to new, so you can add up two photons and get uh, uh, the energy of the radiative photon will be twice of that, and wavelength will be half, right? I mean like that. So with this we can, means Professor Datta has not gone into far, but this is what we require at this moment with the Raman spectroscopy. And I will ask you to read the Banuel's book for more details in the Raman spectroscopy, the parts we have been discussing. So the three take-home messages are: one, that for Raman spectroscopy, excitation wavelength doesn't depend. So, is not, it's not relevant, I should not say. independent, right? Radiation wavelength to two kinds of scattering, Stokes and anti-Stokes, right? And it is opening the realm of two photon absorption when you look at the transition moment integral. Okay. When we are considering the upward transition from the virtual state. Okay. Then actually Sarah has discussed mostly the now Sarah started the discussion about the symmetry. I'm not going into that. We will do it maybe on the next week. We'll do a thorough discussion on the symmetry and we'll solve the assignments. But for now, what I'm going to do is that I'm going to solve a set of numerical problems, not only numerical, but the means I'm going to discuss some model answer, may you can say, or the question paper of mid semester examination question paper of CH442 course that for this semester actually. This was taken by Professor Datta at IIT Bombay, Department of Chemistry. So he has he has given me permission to solve this question set, and let us do that. So the first question is calculate. So there are a set of question. Question one has some set of question from mostly from the rotational spectroscopy and how to record a spectra, that grading and all. So let us solve this question. So question number one actually deals with calculate the bond length of a diatomic molecule AB given that the mass of A and B are 5 mu and 40 mu respectively. Spacing between two successive lines in the microwave spectrum of AB is 8 centimeter inverse. So let us calculate the bond length. We know how to do that. So question 1, we have A and B, given that A is 5 AMU and B is 40 AMU. So we already know if we need to convert it to a two body problem to a one body problem, so we need to get the reduced mass, right? Reduced mass is mass, so this is mass of A and mass of B. So reduced mass is MA by MA plus MB, which is nothing but 200 by 45, that is 40 by 9 AMU. Okay, now that is the thing we understood. Now we know we have a rotational constant B equals to H, Planck constant, by 8 pi square mu not square C, right? So from here you can see your R naught is going to be root over 8 pi square mu B multiplied by C, right? This. What is then you need to know the value of B, but it is already given that spacing between the two successive line in microspectrum is AB. That is, of AB is 8 centimeter inverse, and we know that let me write it, spacing between two successive, how much is that? 8 lines is 8 centimeter inverse, so your 2B is 8 centimeter inverse. Okay, in microwave spectra it is given. So today we discuss Raman spectrum, right? So if Raman spectrum, if the spacing between two successive line is given 8 centimeter inverse, then what would be the B? So actually then it would have been 4B, right? So we need to be very careful about this. So your B is 4 centimeter inverse. Okay. Now let us then calculate what is the value of R0. So we know H is 6 into 6 to 6 into 10 to the power minus 34 joule second, and we can write joule second as kg meter square second inverse. I will take a root like this, and 8 pi square is 3.14 square. Then mu I got it 40 by 9 a mu. From a mu I want to go to kg. I have to multiply it 1.66 into 10 to the power minus 27 kg. Okay. And then the value of B is 4 centimeter inverse. So I will take my uh, velocity of light is also in the centimeter unit, so that I could cut it, right? Centimeter second inverse. So from here you can see that I can cut centimeter inverse, second inverse, centimeter with centimeter inverse, kg with kg, and meter square is left. So means when we take the root, it will become meters, right? So let me calculate the value, and I will tell you that what is coming in meters. 6.626 into 10 to the power minus 34 divided by 8 divided by 3.1 divided by, so this is giving me something around 9.49 into 10 to the power minus 21 meter square, and I have to need to take the root of this, and this is going to be 9.74 into 10 to the power minus 11 meter, which is nothing but 0.974 angstrom, or someone can write it as 97.4 picometers. Okay, so there could be multiple, and means you can use your own unit, and this is going to be the answer of the first question, and you could easily mark 3. Okay, now the second question, question 1AB, is saying that how will the spectrum of the molecule in question 1A change if the temperature is lowered to 0 Kelvin? See, we right now we have the spectrums. What they have asked, that the spectrum is Like, I am not talking about the intensity maybe right now. Suppose I am talking about the intensity. So the gap is 2b, which is 8 centimeter inverse, and there could be multiple intensity could be. Oh, so I'm not going to the details of the intensity. Maybe let me increase it a little bit more, and then suppose it is decreasing. So this is the gap is 2b, that is these are equispaced, which is 2b, right? Now this was the spectrum earlier. And what about, so from where this has started, from j equals to 0 to j equals to 1 delta j, it is the energy gap was how much? Uh, the delta E for this is J for microspectroscopy is 2b into j plus 1. So for j equals to 0 it was 2b. Now this is 4b, 6b, 8b, like this, right? So in a gap, so gap of between the spectrum is 2. Now um, the question is, what will happen to this spectrum when the temperature become absolute 0 or 0 Kelvin? Okay, so let us see. So I will draw the spectrum once again maybe, but not to that details. So this is the spectrum where suppose this is new bar, this is 2b, the first, 4b, 6b, 8b, 10b, 12b. Okay. Now a spectrum at, let us see what will happen to the population. Population of, what is population? Population is dependent on two things, right? One is your the degeneracy factor, and another is Boltzmann distribution, which is given by exponential minus E j of that state by kBt. And your formula of maximum population from this k comes to be, when you take a derivative you are going to get root over kBt by 2 HCB minus half, and at t equals to 0 Kelvin you are going to see that your maximum population J max is, mathematically it will come minus half, but as you know this has some the assumption we took to for the derivation and J max was that the spectrum is continuous, which is not. So actually your J max is actually 0 at 0 Kelvin temperature. So all of your population at 0 Kelvin is at, so maximum population is now shifted to your so population is shifted to J equals to 0 at T equals to 0 Kelvin, and accordingly, according to selection rule, delta J equals to plus minus 1, you can see that now only J equals to 0 to J equals to 1 transition is possible. That is one spectrum, one line. Let me write it in a clear thing. Rotational spectrum one line only, and that is that too from 0 to 1. So the position of that line will be 2b, right? So from this only 2b is possible. Not only population, not only maximum population, all the population is shifted to R. So this is at suppose room temperature. This is at 0 Kelvin temperature, where 2b is actually 8 centimeter. B is 4 centimeter, right? So your only one line is going. You are going to see only one line, that is at 8 centimeter inverse. Okay. So that is what going to happen to your rotational spectrum. Now question number C. Question number C tells us that the energy of a non-rigid rotor in centimeter inverse is given. Ej is B into J into J plus 1 into minus D into J square minus J into J plus 1 whole square. So first question is, what is the starting point of the derivation? So starting point of derivation for the correction to the energy of a rotor due to the non-rigidity. Please note that you are not required to do entire derivation in order to answer this question. And how is second question will be how the rotational spectrum is going to affected due to introduction of this correction term. Work out the relevant expression required to support your answer. The first question is only for 1 mark, that what is the starting point of the derivation, and second part is consist of 2 mark, that what is going to happen to the rotational spectrum due to that D into that introduction of that non-rigidity thing. Okay, let's see question number 1. Question number, what is it? Sorry. Okay. So see the correction term, why the correction term is coming. So when it is rigid rotor, in case of a rigid rotor, the assumption is no change in the bond length due to rotation. So it is going to be fixed, the bond length. So that is one assumption we took. Okay, but in case of, however, in case of non-rigid rotor, the suppose it is uh, rotating like this is enter, this is your one body problem, and it is rotating in this side. So this was the R0, but due to this rotation, now there could be change in bond length from the equilibrium bond length, or what is R0. So this can, there would be a change, and due to that change, and that is going to affect, right, and that is, and there is going to be a centrifugal force, right, acting on this. So that centrifugal force, actually this correction, so the correction term, correction to the energy will be derived from the centrifugal force acting on the mass okay, and it will actually balance this change, which is that force. It is actually the force due to that change in the bond length, which is so this is what they want to. Actually, your energy is going to decrease by minus half k into r minus r0, and you, so from there actually I'm not going into the details of the derivation, but suppose actually there is a term minus half k into r minus r0 square. Okay, so you are going actually, what you are going to do, suppose this minus term is not there, so from here actually we are going to get k square r minus r0 square is actually mu square r square of 4, and like that also going to take uh, something you are going to do to get the angular momentum to the power 4. Okay, so I'm not going to the details of that. uh, Maybe on the next day I'll show it to you. Okay, now let us go to the next part, that what is going to happen to the rotational spectrum due to this correction term. Effect on the rotational spectrum due to non-rigidity. So you know that already given also that Ej is B into J plus 1 minus D into J square J plus 1 square, right? What about Ej plus 1? Bj plus 1 into J plus 2, right? And what is going to happen to this? J plus 1 square and J plus 2 square. What is going to the energy difference going from J plus 1 from J? So that is going to be Ej plus 1 minus Ej, right? So this is going to be Bj plus 1 J plus 2 minus D J plus 1 square J plus 2 square minus B into J plus 1 minus D into J square into J plus 1 square. Actually this is going to be plus, right? Now I'm going to take some commons, that I'm going to take B into J plus 1 term common from the first, so I'll get J plus 2, and from here I'm going to get only J. Okay, what about the square terms? From there also I can, okay, happen maybe, okay, rejoin. And this term is, I am going to take common D into J plus 1 square, so I am going to get J plus 2 square minus J square, which is going to give me 2B J plus 1, from here J this part con, and from here D into J plus 1 square, and from here J square plus 4J plus 4 minus J square, which eventually will give me 2B J plus 1 minus 4D J plus 1 cube. And what about uh, uh, for for rigid rotor? Your delta Ej gap is only 2B into J plus 1, right? So as you can see, your energy, so your energy gap is going to increase by vector of 4D j plus 1 cube. D is very small, but the effect will be prominent at higher j values. Let me show you mathematically what I am trying to say. So suppose these are the rotational spectrums. Not equivalent displaced. Okay. Suppose this was starting 2B, 4B, 6B, 8B, 10B, 12B, 14B, 16B. Okay. And those were equispaced in case of rigid rotor. Now suppose I am shifting this to this color maybe. What will happen to when it is non-rigid? Let me use a dashed line. So there will be very less shift for red shift. So this is a energy scale, right? So in wavelength scale there will be a red shift. So because the energy is decreasing, so wavelength will be increased. So there will be a red shift in the wavelength scale. As you can see, the first for j equals to 0, the change is very less. Now what will happen to for j equals to 1? So the change is a little more prominent, and 6p it is further prominent, and 8b it is prominently blue shifted. For 10b it is also prominently blue shifted. 12b it will also be prominently blue shifted. For 14b it will be blue shifted here. Maybe for 16b it will be here. So your one thing that it is going to decrease, and another thing is, suppose let me write it also here, that rate for rigid non-rigid. Now also the delta Ej is going to be is not going to be equispaced. That is another point. So there are multiple effects. One, that there is a redshift of the spectrum of the lines. There is a redshift in the lines, and the energy levels are not equispaced. Not going to be, if the lines are not going to be equispaced. Okay. We have answered this part. Now let us see what about the D part. So D part is based on that grating question. What is going to be the order of the magnitude of spacing between two successive lines in a grating that is used for a electronic spectroscopy for UV visible region, and why? This is 2 marks. The question is, what is the order of magnitude of spacing between two successive lines in a grating? So we know the formula, right? So we have discussed in the class that your n lambda is into d into sin I plus sin r, where n is your order of diffraction, lambda is your wavelength, d is spacing between the lines in grating, I is incident angle, r is angle of reflection. Okay, now see this equation, let us consider first order diffraction only. So the equation becomes lambda is equal to d sin I plus sin I. Let us also take assume that the maximum value of I is 1 and sin r is 1. So you are going to get lambda is equal to 2d, or your spacing is going to be lambda by 2. So for UV visible spectroscopy, the wavelength range is actually 200 to 800 nanometers. Okay, so as you can see, your D could be from 100 to 400 nanometer. There is a possibility. So actually, if someone write the spacing between the lines of the grating should be in few hundreds of nanometers, right? For UV visible spectroscopy. So that's all one have to write to get these 2 marks. Okay. I think someone is joined, or our meeting link is getting once, stay in the call. Okay. So we have another question to solve, and we are going to solve 2 more questions. Okay. So the first question, question 2a, why is the fundamental transition for an enharmonic oscillator is much stronger than the fast overtone? Very good, important question. Okay. Why is the fundamental transition? Fundamental transition is from v equals to 0 to 1, and the fast overtone is v equals to 0 to 2. To answer this question, we need to invoke that earlier, when the enharmonicity was not there, it was a harmonic oscillator. But now, when we take into the perturbation into the picture, perturbation in the real thing, where we are, so from harmonic to enharmonic, we are actually So actually it behaves like an harmonic oscillator, close to an harmonic oscillator, but we have started from harmonic oscillator. So we are actually to the ideal system we are giving some perturbation, and that unperturbed wave function is, suppose for v equals to 0 is something is unperturbed, but that perturbed state can also be written into a linear combination of that unperturbed state and the other unperturbed vibronic states. How? Let me show you. So we can write the functions of the in a following manner, that is, suppose the for this is for the perturbed system. These all we are discussing for the perturbed system. Okay, all perturbed. So this perturbed psi v equals to 0 can be written as a wave function with the unperturbed zeroth v equals to 0 plus a combination of I which is not equals to 0. So other unperturbed wave function, okay, with certain amplitudes, right? Similarly, the perturbed wave function for v equals to 1 can be written as the unperturbed wave function with, suppose now it is not I but j not equals to 1, the other unperturbed wave functions and their contribution is, or their coefficient is bj. Okay, and what can we write about v equals to 2? Same, k not equals to 2 ck psi v equals to k unperturbed. So near combination of the means the perturbed function can be expressed into a linear combination of the unperturbed wave function and unperturbed wave function and closely related unperturbed wave function, right? So now for fundamental transition, that is the transition moment integral v equals to 0 to b equals to b equals to 0 to b equals to 1. So that is the transition moment integral is 0, right? Now this can be written. Now I will break this part. Right? Now I will break these terms in different color. Okay, one component is going to be like this, another component will be bj. Okay, I made one mistake. And there will be another component. So let us discuss the fate of these components. As you can see, this, as it is from v equals to 0 to v equals to 1, and our we know the selection rule is v equals to plus minus 1, right, for unperturbed systems. So this actually is going to have a significant finite value. What about this? As this, I also should write that this AI, BJ or CK are very small. So these are small finite value when, only when j equals to 1, else 0, right? Because only delta v equals to j is possible. What about this? So this is also small finite value only when I equals to 0 or 2, else 0, right? And this is also same, very small. That too j equals to I plus minus 1, else 0. So but it has a significant contribution from the first part. Okay, now let us see what is going to happen for the fundamental the first overtone. For first overtone, that is the transition from v equals to 0 to v equals to 2. So TMI psi v equals to that is 0 plus k naught equals to 2 ck psi v equals to k 0th psi v equals to 0th plus summation of k to 0 not k but I, right? AI psi v equals to I 0th. So from here also you are going to get 4 terms. I will write one by one. First term is between psi v equals to 2 okay. So this is one term. Now the next term is k not equals to 2ck I equals to K zeroth here this is not equals to 0. Okay, I was just checking if I have done any mistake in the earlier case like this. So this AI is outside. B equals to 2 zeroth. B equals to I 0. Then there will be another part. That is I not equals to 0. K not equals to 2. AI CK I B equals to K zeroth mu I B equals to I zeroth. Now let us discuss what is the fate of this going to be. If you see, this is going to be actually 0. Why? Because delta V is 2 in this case, plus 2. Okay, that's why this is going to be 0. So it don't have any contribution. Earlier in case of it was delta V equals to plus 1. That's why it has a significant value. What about this? But this also small finite value when only when K equals to 1 else 0. What about this? This is also true. Finite values only when I equals to 1 or 3 else 0. This also gives us very small finite value only when K is I plus minus 1 else 0. So when I compare now at the transition moment calls for and fundamental and fast overtone. We are going to see TMI for fundamental is greater than TMI fast overtone. Okay, and that is why the intensity of fundamental is much greater than intensity of fast overtone. See, the fast overtone is coming due to this perturbation, only due to this enharmonicity, right? And that time, this, for the unperturbed part, it is going to be zero, right? For the all the unperturbed part, when only because of these terms, these and these, when they are in a particular I is equal to 1 or 3 or k equals to 1 or these particular conditions, there is going to be a very small finite value of the TMI, and that is when your V equals to plus minus 2, V equals to plus minus 3, these kind of over. That is why these overtones are possible in case of the enharmonic oscillator, which was not possible in the case of unperturbed harmonic oscillator. Okay. So I hope you get a clearer idea right now, and let us do another question, question 2b, and with that we will end, because the question 2c actually was already solved in the, so that is actually a derivation question and actually solved in the lectures. So we will not go into that. Let us do the last problem, question 2b. And question 2b is saying that using a Taylor series expansion of the potential energy of an enharmonic oscillator, you need not know the expression for the coefficient, use C1, C2, C3, etc., and arrive at the energy expression considering the first order correction only. So you need to take a Taylor series expansion of the potential energy of the enharmonic oscillator. Let's do it. And we have to arrive at the energy expression that with the first order energy consideration only. Let's see. So potential energy can be written of the enharmonic V can be written as C0 C1x plus C2x square plus C3x cube plus C4 to the power 4, and these will go on. This is the Taylor series expansion. Now we already know that for harmonic oscillator, these C0 and C1 is already 0, and V is this C2x square, or you can say half kx square, right? See here C2 is a constant, so we can write it. So it has this quadratic term. So this x cube, x to the power 4, these are going to be the perturbation term from harmonic to enharmonic. Okay. So we need to consider I greater than 2, that will contribute to the perturbed energy expression. Okay. Now the perturbed energy with first order correction, if you remember, is given by integral between to the perturbation v equals to 0, and your here the perturbation is actually C4 x to the power 4 psi v 0, and this will go on. Okay. Now see, so from here we can see we need to solve this, or we need to get the integral values. But how can we do it easily? Let us see. We need to consider that what is the means what is these integrals individually as symmetric or antisymmetric, the integrand, and based on that we can reach this easily. Okay. Irrespective of the symmetry of the psi v0, the triple product or integrand will be symmetric when the perturbation is symmetric and the integrand will be anti-symmetric when the perturbation is anti-symmetric, right? Because anyway those psi v0 antisymmetric will lead to symmetric, and symmetric will also lead to be symmetric. It will depend on the symmetric of the perturbation only. So in case of I equals to odd, integrand is antisymmetric, hence the integral is 0. In case of I equals to even, the integrand is symmetric, and integral is non-zero. So only those terms are going to contribute. Only I equals to even terms are going to contribute in the energy correction. And ultimately, you know, the energy correction becomes, right, that v plus half nu mu by minus b plus half square mu by xc, right? So this comes from the only the x to the power 4, and if you consider the other x to the power 6 and x to the power 7, those kind of things, then you are going to get more. So I'm not solving the question to C. I hope you understood a lot from these questions, the answer from these questions. Why the transitions are weak for the overtones than the fundamental transition. We took it axiomatically till now, but we have solved it. We have shown it with the TMI, the transition movement integral also, and the other problems. Hope this was with this today we are going to finish today's session, the week 7. I hope this was a useful session to you, and I hope to meet you all in the next session. And with that, today we are going to stop. Thank you. Thank you for listening.